I am JV and Dr. Surendra Kumar Srivastav from the Department of Science under the Faculty of Education and Methodology, Jayoti Vidyapeeth Women's University, Jaipur. Today I will discuss the bilinear transformation or Mobius transformation. A transformation of the form W is equal to AZ plus B upon CZ plus D is called the Mobius or bilinear transformation of linear fractional function where a, b, c, d are complex constant. Such type of transformation was first studied by Mobius and hence sometimes it is also known as the Mobius transformation equation. And the above equation can be written as CWZ plus DW minus AZ plus B is equal to 0, which is linear in W and Z both, so it is called the bilinear. Now we see the theorem. Prove that the cross ratio remains invariant under a bilinear transformation. Let W1, W2, W3 and W4 be the images of four distinct points Z1, Z2, Z3, Z4 respectively under a bilinear transformation. W is equal to AZ plus B upon CZ plus D equation first. If we show that W4 minus W1, W2 minus W3 whole upon W2 minus W1, W4 minus W3 is equal to Z4 minus Z1, Z2 minus Z3, Z2 minus Z1, Z3 minus Z4 minus Z3, then the result will follow. From first, WR minus WS is equal to AZR plus B upon CZR plus D minus AZS plus B upon CZS plus D. Now solving by LCM, this is AZR plus B, CZR plus D minus AZS plus B and CZR plus D whole upon CZR plus D and CZS plus D. After multiplication and solving, we can find WR minus WS is equal to ZR minus ZS in bracket AD minus BC whole upon CZR plus D and CZS plus D. So W4 minus W1 and W2 minus W3 is equal to Z4 minus Z1 AD minus BC, Z2 minus Z3 AD minus BC whole upon CZ4 plus D and CZ1 plus D, CZ2 plus D and CZ3 plus D. So W4 minus W1, W2 minus W3 is equal to A minus D, AD minus BC to the whole of square in bracket Z4 minus Z1 and Z2 minus Z3 whole upon CZ1 plus D, CZ2 plus D, CZ3 plus D and CZ4 plus D. This is equation A. Now the similarly W2 minus W1, W4 minus W3 is equal to AD minus BC to the whole of square Z2 minus Z1, Z4 minus Z3 whole upon CZ1 plus D and CZ2 plus D, CZ3 plus D and CZ4 plus D. This is equation B. Now A dividing by B, then W4 minus W1, W2 minus W3 whole upon W2 minus W1, W4 minus W3 is equal to Z4 minus Z1, Z2 minus Z3 whole upon Z2 minus Z1, Z4 minus Z3. Hence cross ratio remains invariant under a bilinear transformation. Hence proof. Now we see a problem which is depend on this formula. Find the bilinear transformation which maps the points Z1 is equal to 2, Z2 is equal to I, Z3 is equal to minus 2 into the points W1 is equal to 1, W2 is equal to I and W3 is equal to minus 1. For the solution, we know the required formula is W minus W1, W2 minus W3 upon W1 minus W2 and W3 minus W is equal to Z minus Z1, Z2 minus Z3 upon Z1 minus Z2 and Z3 minus Z. Putting the values of W1, W2, W3 and Z1, Z2 and Z3 and find W minus 1 upon W plus 1 is equal to Z minus 2 upon Z plus 2, 2 plus I upon 2 minus I, 1 minus I upon 1 plus I. So we can solve z minus 2 upon z plus 2 after multiplication by the conjugates by the denominator. So we get z minus 2 upon z plus 2 in bracket 3 minus 4i upon 5 and second bracket minus 2i upon 2. Finally, this can be written as z minus 2 upon z plus 2 in bracket 4 minus 3i upon 5. Now by componendo and dividendo, this can be written as w minus 1 plus w plus 1 upon w minus 1 minus w minus 1. This is 4 minus 3i z minus 2 plus 5 z plus 2 upon 4 minus 3i z minus 2 minus 5 z plus 2. After solving this, we can find w is equal to 3z plus 2i upon iz minus 6. Now there is a question: find the bilinear transformation which maps 0 I minus 1 of the plane to 1 minus 1 0 of W plane. This question will be solved by you. Now we see the another problem. Find the bilinear transformation that maps the point z1 is equal to infinity and z2 is equal to I and z is equal to 0 into the points w1 is equal to 0, w2 is equal to I and w3 is equal to infinity. For the solution, let the transformation be w minus w1, w minus w2 minus w3 whole upon w1 minus w2 and w3 minus w is equal to z minus z1, z2 minus z3 upon z1 minus z2 and z3 minus z. Substitute the given values of w1, w2 and w3 and z1, z2 and z3. Finally, we get w upon I is equal to I upon z. So this can be written as w is equal to minus 1 by z. Now the next problem, so that the transformation w is equal to 2z plus 3 upon z minus 4, transform the circle x square plus y square minus 4x is equal to 0 into the straight line 4u plus 3. It is given that w is equal to 2z plus 3 upon z minus 4. This is equal to wz minus 4w is equal to 2z plus 3. So wz minus 2z minus 4w minus 3 is equal to 0. Again, this can be written as z is equal to 4w plus 3 upon w minus 2, or z bar is equal to 4w bar plus 3 upon w bar minus 2. We know the equation of circle is x square plus y square, x square plus y square minus 4x is equal to 0, or in complex form this can be written as z bar minus 2 in bracket z plus z bar is equal to 0. So this can be written as 4w plus 3 upon w minus 2, 4w bar plus 3 upon w minus 2 minus 2 in bracket 4w plus 3 upon w minus 2 plus 4w bar plus 3 upon w bar minus 2. Okay, after solving by LCM, this can be written as 16w bar plus 12w plus 12w bar plus 9 minus 8w bar plus 16w minus 3w bar plus 12 minus 8w bar plus 16 bar minus 6w plus 12. After solving, we can find 22 in bracket w plus w bar plus 33 is equal to 0, and we can write 22 w plus w bar can be written as 2u. This is since w is equal to u plus ib and w bar is equal to u minus ib. After solving, this is 2u is equal to w plus w bar. So w plus w bar can be replaced by 2u. Finally, this can be written as 4u plus 3 is equal to 0, which is the equation of straight line in w plane. Hence, required result follows. Thank you.